Right, let's get started. Okay, I sent out an announcement. There are some new assignments posted on mastering. Okay, also, I'll send out an email reminder, but next week there's a holiday on Wednesday, and so both Monday and Friday are going to be all remote.
Do we not have class on Wednesday?
It's a holiday. It's a Veterans Day. So, yeah. Right. Next Wednesday, the 11th. Okay, we'll go ahead and get started. Okay, when we left off, we were looking at methods of preparing alcohols. I'm going to briefly review the properties and nomenclature. Okay, alcohols will end in all. Alcohols have some similarity in structure to water. They have the bent OH bond, but it's to a carbon on one side rather than an oxygen, rather than a hydrogen, sorry. Make sure you know how to classify alcohols. Okay, there's also methanol, which is by itself, but methanol in some ways behaves like a primary alcohol. Okay, these are classified according to the number of carbons directly attached. Oh, I'm sorry. You know what, I'm not sure I'm sharing my screen. Let me just double check here. Yeah, sorry about that. I need to share my screen. Okay.
Last Wednesday, I think we were also having troubles with like the microphone hearing us. I don't know, because I had asked a question and I don't think that like your sound was on or something.
Yeah, I couldn't hear anyone. Okay. I don't know why that was last time.
I just wanted to let you know in case they couldn't ask a question or anything.
Yeah, okay. Okay, so anyway, make sure you know how to classify alcohols, because some classes of alcohols will undergo some reactions which others will not. In many ways, the reactions of phenols are quite different from those of alcohols. That's why they're a separate category. Okay, these are the four categories, examples of the four categories: primary, secondary, tertiary, and phenol. Right, alcohols will end in OL. Okay, this one up here is called benzyl alcohol. It's distinctly different from phenol in that it has this extra CH2. Alcohols take priority over alkenes and alkynes and alkyl groups and halogens. Okay, here's an example of an alcohol that also has an alkene group. Okay, so we would name this as pent-4-ene-2-ol. Okay, the ene is located at 4. The 2 is the location of the ol group. Okay, we haven't. We'll cover amines next semester, but amines are below alcohols. But alcohols are above alkenes and alkynes, and alkanes and ethers and halides. Right. Carboxylic acids.
Dr. Trump?
Yeah.
Can you let someone in from the waiting room?
see. Hold on. Okay. Okay, I'm just trying to see where that is. Um, here. Okay, I'm not. Oh, okay, yeah, I see someone. Okay, there's one. Okay, there we go. Okay, so if a compound contains a higher priority group, okay, such as acid, ester, aldehyde, or ketone, then the alcohol is a hydroxy. Right? If the alcohol is the primary functional group, we don't use hydroxide, we use all. Okay, these are some common names. These are still very widely used commercially: isobutyl alcohol, sec-butyl alcohol. If we have two alcohols present, that's a diol. Okay, both alcohol groups need to be located. 1,2 diols are called vicinal diols or glycols. When an OH is directly attached to a benzene ring, that's a phenol. Okay, alcohols have high boiling points because of hydrogen bonding. Small alcohols are miscible in water. Solubility decreases as the size of the alkyl group increases. Okay, boiling points also increase as the size of the alkyl group increases. Okay, this is a comparison of ethanol, dimethyl ether, and propane. Okay, propane is associated only by London dispersion. Its boiling point is -42. Dimethyl ether does have a dipole moment, okay, because of the bent geometry around the oxygen, but it does not hydrogen bond. Okay, it has the same molecular formula, the same molecular weight as ethanol, but ethanol boils at a much higher temperature, 78. Okay, so hydrogen bonding is prevalent in alcohols. Okay, this chart shows that solubility in water goes down as the size of the alkyl group increases. Diols tend to be very soluble. For example, hexane 1,6-diol is miscible in water, whereas something like hexane 1-ol would be much less soluble. Here's N-pentyl alcohol, 2.7% soluble. Okay, and as the size of the R group, oh, here's hexyl. Okay, that's only 0.6% soluble. Okay, last time I talked about some details about commercially important alcohols like methanol and ethanol, what an azeotrope is. Propan-2-ol or isopropyl alcohol is used in rubbing alcohol. It's also a good solvent in the laboratory. This is how it's made commercially, by hydration of propylene. Most acidities are a little bit weak. Most alcohols are a little bit weaker in acidity than water. Phenol is very different. It's 100 million times more acidic than cyclohexanol. Okay, water's 15.7. You can see most of these alcohols are less acidic. If there are electronegative elements like chlorine nearby, okay, those are going to raise the acidity. 2-chloroethanol, 14.3, 2-trichloroethanol, 12.2, and then phenol is 10. Okay, I'm going to review this again briefly. One of the ways we can generate the conjugate base, and this is what we commonly do in the laboratory, is to react an alcohol with an active metal like sodium or potassium. Okay, even though we produce the conjugate base, this is not an acid-base reaction, but rather it is a oxidation reduction reaction. Sodium gets oxidized, it loses an electron. Hydrogen gains an electron, so it gets reduced. For 2-propanol and tert-butyl alcohol, you usually use potassium rather than sodium. Okay, they're less acidic. Potassium is more reactive than sodium.
What is the arrow by the hydrogen?
That indicates a gas. Okay, that would mean the same thing as means the same thing as that. So the arrow indicates a gas. Okay, when you put sodium in ethanol, for example, you'll see bubbles of hydrogen gas come off. All right, phenols can be easily deprotonated using sodium hydroxide. Okay, because they're much more acidic than alcohols. Okay, but not as acidic as carboxylic acids. Okay, the reason for the acidity, resonance. Okay, the negative charge is delocalized or spread all the way around the ring. Okay, these are reactions we've looked at so far. Okay, we can prepare alcohols by nucleophilic substitution, SN2 of alkyl halides. We can hydrate double bonds, either Markovnikov or anti-Markovnikov. We can make diols, either syn or anti-dihydroxylation. Okay, syn dihydroxylation is done using osmium tetroxide or cold dilute potassium permanganate. Anti-hydroxylation is where we make an epoxide using something like MCPBA, and then we hydrolyze it in acid or base. Okay, now we'll look at organometallic reagents. Okay, when carbon is bonded to a metal, okay, such as magnesium or lithium, carbon is more electronegative than the metal. Okay, metals are typically electropositive. And when we form an organometallic with magnesium or lithium, it can attack alkyl halides or carbonyl compounds. We're going to focus more on the carbonyl compounds. But this is a good way of forming carbon-carbon bonds. Okay, we've seen an example of this so far, and that's carbon-carbon bonds. If we make a sodium acetylide, we use NaNH2 to pull this hydrogen off the end of a terminal alkyne. We get this acetylide, which can do an SN2 on a primary alkyl halide, or this addition reaction. Okay, this attacks the carbonyl, pushes a pair of electrons onto the oxygen, and then once this is done, then we add dilute acid. This will then pick up a proton from hydronium, and we get an acetylenic alcohol. Okay, so that's one we saw in the last chapter. Okay, now we're going to introduce the idea of Grignard reagents. Grignard reagents, the Grignard reaction, was named after the French chemist Victor Grignard. And Victor Grignard won the Nobel Prize in 1912 for the discovery of this. That was over 100 years ago. The Grignard reaction is still used today very extensively. Next semester, I'm planning to do a Grignard reaction in lab. Okay, so if we take an alkyl halide, or R can also be a benzene ring. Okay, so this could be bromobenzene or something like that. And we react it with magnesium metal. And the solvent here is important. Most commonly, it's done in ethyl ether. Turns out that the oxygen on the ether coordinates the magnesium and helps stabilize the Grignard reagent. So solvent does matter here. Okay, magnesium will insert itself between the carbon and the halogen. Okay, so we'll have this organomagnesium halide. Okay, this causes a reversal of polarity. Okay, you know that halogens are more electronegative than carbon, and so they're pulling electrons away from the carbon, so the carbon is partially positive. Okay, when we insert a magnesium, that reverses the polarity. Now, electrons are being pulled toward the carbon instead of away from the carbon. And so this acts like a negatively charged carbon, a carbanion. And so carbon went from electrophilic to nucleophilic. Iodides are the most reactive. Okay, you can use bromides. Chlorides in some cases are not reactive enough. They can be used in some situations, but fluorides generally do not react. So X is fluorine, chlorine, bromine, or iodine. Okay, we can use the Grignard reagent to form primary, secondary, or tertiary alkyl halides. Okay, so here are a couple of examples. Using bromobenzene, we can make phenyl magnesium bromide. Okay, using 2-chlorobutane, we make sec-butyl magnesium chloride. Again, magnesium inserts itself. Okay, so this shows the reversal of polarity. Okay, here you can see the carbon is surrounded by this blue area. Okay, it's electrophilic, whereas the halogen is electron dense, it's red. Okay, when we insert a magnesium, okay, notice the color change here. This is now electron dense. The magnesium is very electron lacking. So carbon is pulling electrons this way. All right, we can do the same thing with lithium reagents. And I've used this reaction a lot in my research using lithium. Lithium is more electropositive than magnesium, so organolithium reagents react faster than Grignard reagents. Okay, so using 2 equivalents of lithium metal, okay, we form the organolithium and then we form the lithium halide as a byproduct. And again, the electron pair is skewed toward the carbon, so this reacts like a carbanion. Reacts the same way as a Grignard, but reacts faster. In this case, ether is not necessary. We can use a wide variety of solvents as long as they don't have acidic protons. So we could use hexane or something like that as a solvent. Okay, and here's just a few examples of organolithium reagents. We can make butyllithium or vinylithium or phenylithium from these different halides. Okay, so Grignard reagents, since carbon is now nucleophilic, can add to the carbon of a carbonyl. Usually an aldehyde or ketone. We'll talk about esters later. We'll start off by looking at aldehydes and ketones. We form a bond. Okay, this pair of electrons then shifts onto the oxygen. And then in the second step, we'll add dilute acid to protonate this, and we'll get alcohol. Okay, this is an extremely useful reaction. We can build just about whatever carbon skeleton we want. Yeah.
I was just curious. So the organolithium slide that we were just on, now I know that lithium is used for a lot of bipolar medications.
Yeah. Yeah.
Are those organolithium molecules or?
Okay, the question was about lithium in bipolar medications. Usually that's inorganic lithium. It's usually something like lithium carbonate. Yeah, these lithium reagents would be much too reactive to use in medications.
What would they use to them?
These?
Yeah, like what would?
You would do exactly the same thing as you're doing here with the Grignard. You can form new carbon-carbon bonds.
Gotcha.
Yeah. Also, something like butyllithium is an extremely strong base. So we could remove protons that would be difficult to extract otherwise. Butane has a pKa of about 50, so the butyllithium is an extremely strong base. Okay, so here's the general reaction. R minus can be a Grignard or an organolithium. Does the same thing. This has to be done in 2 separate steps because if you introduce the hydronium here, that's going to immediately react with your Grignard or lithium reagent. Right, so if we use formaldehyde as our starting material, okay, the Grignard forms a new bond with the carbon, and then we end up with a primary alcohol. Okay, this was a CH2, and then this is now CH2OH. If we use some other aldehyde other than formaldehyde, we'll get a secondary alcohol. If we use a tertiary alcohol, if we use a ketone, we'll get a tertiary alcohol. Okay, same mechanism. Okay, so the Grignard attacks the carbonyl carbon, forms a new bond, and then once that reaction is complete, then we'll add dilute acid and we'll form an alcohol. Okay, so this problem is show how you would synthesize the following alcohol from compounds containing no more than 5 carbon atoms. Okay, on board here, I'm going to redraw this. All right, so this time, this is a product we're working backwards. And the way you would break this down is you locate the CO bond, okay, which is right here. And then you break the next carbon-carbon bond. Okay, there's actually 3 ways that we could break this. We could break it here, we could break it here, we could break it here. The problem specifies using no more than 5 carbon atoms. Okay, so if we break it here, all right, the part without the oxygen would be our Grignard, and then part with the oxygen right, we would remove the H and make this a double bond. Okay, so we can propose 3 different ways of doing this. I've shown you one. Okay, so we could break it at the ethyl. That's the first method. We could break it at the methyl. Okay, and then we would have this ethyl cyclopentyl ketone and the methyl magnesium bromide. And then the third way is what I've shown you here, is we could have the methyl ethyl ketone and the cyclopentyl magnesium bromide. Okay, any of these syntheses would probably work, but only the third begins with fragments containing no more than 5 carbon atoms. Right, Grignard reagents can react with acid chlorides and esters. The difference here is that the stoichiometry is 2 to 1. Okay, the ester or acid chloride will react with 2 equivalents of Grignard, and it will add 2 identical alkyl groups. Okay, so this is an acid chloride. It adds 2 equivalents of Grignard, and so we'll get a tertiary alcohol. There's an R prime attached to the acid chloride, and then we'll add 2 R groups. Okay, same way with an ester. Okay, the OR double prime is no longer there. The chlorine is no longer there in the product. Okay, so this is what happens. Okay, it's actually the same mechanism for an acid chloride and an ester. Okay, so again, the Grignard attacks the carbonyl. We get this tetrahedral intermediate. The intermediate collapses, oxygen pushes toward the carbon, kicks out the chloride. Chloride's a good leaving group, and we get a ketone. Okay, we just saw that ketones will react with Grignards. So the ketone that we produce will react with the second equivalent. Okay, so here is the ketone. Reacts with the second equivalent of Grignard. Okay, once this reaction is complete, then we add dilute acid, and we end up with a tertiary alcohol with two identical groups. Okay, same thing with esters. The only difference is the leaving group is different. Instead of a chloride, we get an alkoxide as the leaving group. Right, so the Grignard attacks, we form this tetrahedral intermediate. Okay, this, again, oxygen pushes toward the carbon, kicks out the alkoxide, we get a ketone. The second equivalent attacks the ketone, and once we protonate that, we'll end up with a tertiary alcohol. Ethylene oxide is not a carbonyl, but it does react with Grignards and lithium reagents. Most ethers will not react with these, but ethylene oxide has a special status in that it contains a strained ring. Okay, so the Grignard attacks a carbon, and that causes this ring to break open. And then once we protonate that, we have a primary alcohol 2 carbons longer than what we started with. Okay, formaldehyde will make a primary alcohol 1 carbon longer. Ethylene oxide makes one 2 carbons longer. Okay, before we go on to lithium dialkyl cuprates, okay, I'm going to share with you the Grignard song. I've had students tell me, for example, they've gone on to medical school and they said they remembered the Grignard song, and it actually helped them to answer test questions. Okay, this goes either to the tune of America the Beautiful or Gilligan's Island. The carbonyl is polarized, the carbon end is plus. The nucleophile with us attack the carbon nucleus. A Grignard makes an alcohol of type Saraba 3 and forms a bond to correspond from C to shining C.
That was really good. Yeah. Just wanted you to know.
Okay, another type of organometallic is the lithium dialkyl cuprate. Lithium dialkyl cuprate is also called a Gilman reagent. If you ever go up to Iowa State University, the chemistry building there is called Gilman Hall. It was named after Henry Gilman that discovered this reagent. Okay, this is made from an alkyl lithium and copper 1 iodide. And this is used to couple two alkyl groups together. Okay, some of the limitations of organometallics, particularly Grignards and organolithiums. Okay, they are good nucleophiles, but they're also very strong bases, which means that you can't have anything that's acidic present. Okay, when you're making a Grignard, for example, or you're using a Grignard, you've got to be very careful to exclude water. In my research, what we'll typically do is we'll fill the reaction vessel up with argon. This will displace water vapor and air as well, and then we'll keep it sealed to keep air and moisture out. Not only water, but anything with an OH, okay, an alcohol, carboxylic acid, anything with an NH, an SH, or a terminal alkyne, any of these are going to react with your Grignard. If there are multiple bonds that you don't want the Grignard to react with, the Grignard is going to react with those. If you have a carbonyl, a nitrile, SO, or NO, okay, any of these will react with a Grignard. Okay, here's what happens if you have water present. You just get an acid-base reaction. So if this were butyl magnesium bromide, for example, you just end up with butane. Okay, butane or other alkanes have a pKa which is greater than 45. And so this immediately picks up an H from water, and that's the end of the reaction. Okay, same way with organolithiums. Okay, you got to be very careful to exclude water. Okay, if there's an NH or a terminal alkyne, again, you're just going to have an acid-base reaction that occurs. All right, now we change to a different subject here. We can prepare alcohols by reduction of carbonyl compounds. A common way of doing this is to use hydride reducing agents. These will add a hydride or H- ion to the carbonyl group. We produce an alkoxide ion with no additional carbon atoms. That is, unlike a Grignard or lithium reagent. Okay, so we produce an alcohol with the same number of carbon atoms. Okay, so reduction of an aldehyde yields a primary alcohol. Reduction of a ketone will yield a secondary alcohol. Okay, so these are common reducing agents: sodium borohydride and lithium aluminum hydride. These are called complex hydrides. They don't have a simple hydride structure such as sodium hydride or lithium hydride. The bonding to the metal makes the hydrides more nucleophilic and less basic. Right, sodium borohydride, or NaBH4, is one source of hydrides. H minus. The hydride attacks the carbonyl carbon, which forms an alkoxide ion. Then we protonate the alkoxide. Sodium borohydride reacts only with aldehydes and ketones, not with esters or carboxylic acids. Okay, so we could reduce a ketone or an aldehyde in the presence of an acid or an ester using sodium borohydride. Right, here's the mechanism. Okay, this looks a lot like a Grignard, except instead of carbon, it's hydride. So hydride attacks, we form a CH bond. We have a CO single bond in the intermediate, and then we add water or solvent to form the alcohol. Right, here are some examples of sodium borohydride reduction. Okay, cyclohexane carbaldehyde, we have an aldehyde here. Ethanol here is the solvent. So this hydrogen right here comes from the borohydride. This hydrogen comes from the ethanol. The H on the ethanol, the H on the O. Okay, butan 2-one can be converted to butan 2-ol. This is a racemic mixture. Okay, we get both enantiomers in equal amounts. All right, lithium aluminum hydride is a stronger reducing agent than sodium borohydride. It is dangerous to work with, which I know from personal experience. It reduces ketones and aldehydes into the corresponding alcohol. It also reacts to convert esters and carboxylic acids to primary alcohols. Okay, when I was a graduate student, I was adding a solution of lithium aluminum hydride. It was dissolved in ether through an addition funnel, okay, a lot like the septory funnels that we use, into my reaction mixture. I was adding it dropwise. The stopcock started leaking. I had the reaction vessel in an ice bath. Some of the lithium aluminum hydride solution dripped into the ice bath. When lithium aluminum hydride comes in contact with water, produces hydrogen gas. It's exothermic, and of course ether is very flammable as well, so we had this big flame that happened.
Did you get hurt, or was there just
No, I got it put out right away with the fire extinguisher, but it just, the whole thing went up in flames.
scared you for a second?
Yeah. Okay, so here's an ester, and this is reduced to primary alcohol. Okay, the mechanism is actually similar to the mechanism for the Grignard attack on esters. Okay, and I'll show you that here. Okay, so we have methyl benzoate. All right, so hydride attacks. And just like with the Grignard, oxygen pushes down, kicks out the methoxy group. We get an aldehyde. Right, and then the lithium aluminum hydride supplies a second hydride. And once this is complete, we get the corresponding primary alcohol. So sodium borohydride can reduce aldehydes and ketones. Lithium aluminum hydride also reduces aldehydes and ketones, but it can also reduce esters and acids. Okay, so if you're going to reduce an aldehyde or ketone, I would choose sodium borohydride. But if you're reducing one of these others, then use the lithium aluminum hydride. Okay, so sodium borohydride, this is a good illustration. You can see that it reacts with the ketone, but it leaves the ester unaffected. Lithium aluminum hydride reduces both the ketone and the ester. Okay, the ester will always produce a primary alcohol. You can also use catalytic hydrogenation using Raney nickel. Raney nickel is hydrogen-rich nickel powder. Sometimes it's mixed with aluminum powder, and it's saturated with hydrogen gas. It's more reactive than palladium or platinum catalysts. Raney nickel also reduces alkene groups. Sodium borohydride, lithium aluminum hydride typically don't reduce carbon-carbon double bonds, but they'll reduce carbon-oxygen double bonds. So it all depends on what you're trying to do. Okay, if you want to selectively reduce the carbonyl but not the alkene, then you can use one of these hydride reagents. If you want to reduce both, then you can use Raney nickel and hydrogen. All right. Okay, so here we have 2,2-dimethyl-pent-4-enal. It has both an aldehyde and an alkene. Raney nickel reduces both double bonds. Sodium borohydride reduces just the aldehyde to the primary alcohol. It leaves the alkene. Okay, I'm going to stop there. Okay, and we'll pick this up again on Wednesday.